Okay, so today's notes are on absolute value and families of functions. Our content objective is to graph absolute value functions and write their equations, as well as describe function transformations, and our language objective is to describe function transformations with correct terminology. So I want to start out by sketching what's called the absolute value parent function. So we'll talk about parent functions more in a second, but the absolute value function is just f of x equals the absolute value of x. So it's a pretty basic function. And it looks something like this. So if you can do your best to sketch this correctly, it'll benefit you later on. We have our x-axis, our y-axis, our origin, and this is where our graph is going to start on the origin there. And I'm going to graph 1, 2, 1, 2, 1, 2, -1, -2, 1, 2, 3. We'll go to -3 and 3 since we have room. So our first thing I want to note is our absolute value functions will have a V shape. That's their signature look, a V shape. And their vertex, which is their maximum or minimum point, depending on which way it opens, starts for the parent function at 0, 0. The slope of this parent function on either side is going to be -1 or 1. So up here, or on the right side, it's going to go up 1 over 1, up 1 over 1, up 1 over 1, and then it's going to do the same thing the other way to make that V shape. So it ends up like this. So as you can see on the left side, our slope is -1. I'm going to use the variable m to represent slope. On the right side, it's 1, so this one goes down, but it's really just a mirror image on either side. So up 1 over 1, up 1 over 1, each direction. So as I mentioned just a second, on either side. As I mentioned just a second ago, this is what's called the parent function for absolute value. So a parent function is the simplest form of a set of functions that form a family. So I'm going to write that out. The simplest form in a set of functions that form a family. And I'm writing this down because we're going to tie this back in. Some of the things we're learning about in the context of absolute value are going to tie back to other functions. But this is the simplest form of our absolute value function. It's the parent function for the absolute value function family. And now I want to talk about how we can build the rest of the absolute value functions in that family. So all absolute value functions are going to take the following form. So f of x equals a, absolute value, x minus h, absolute value, plus k. So all the families of this absolute value function, so this one's the parent function, it's the simplest version. All of the other absolute value functions are going to still have this form. So the only change that's being made here is these three variables, a, h, and k. So what a is going to do, or tell us, a is the slope of the line. So it tells us here we went up 1 over 1 and then mirrored it on the other side. A is going to tell us the slope of the line on the right side. So then we can do the mirror image to make the left side. So A is always going to tell us our slope. H is the x value of the vertex. So again, the vertex is the maximum or minimum point. Here it's at 0, 0. But if we slide it left or right, h will tell us what it's going to be. So h is the x value of the vertex. K then is the y value. So our vertex is always going to be h comma k. So h comma k will always tell us our vertex. So I'm going to do a quick little example here. I want us to graph f of x equals 2 absolute value x minus 1 plus 3. So first thing I wanted to do is determine, let's slide this up, A, H, and K. So A is the number being multiplied in front, that's 2. K is the number being subtracted, that's 1. Notice that it's always the opposite sign of what's in there. So, or sorry, H is 1, my bad, sorry. H is 1, it's always the opposite sign of what's inside the absolute value. So H is 1 here, not -1. The sign switches when you take it out because the original form includes the negative sign. And then K is 3. So K is 3. So now I'm going to plot the vertex. So I need to first make my grid here to do that. So I'm going to make it, so since I know my vertex is a bit higher up, I'm going to go like this. And my x-axis, my y-axis, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm going to plot my vertex at 1, 3. So 1, 3. That is the point for my vertex. Then I'm going to plot more points using slope, which I'm going to determine from A. So I know my right side has a slope of 2. So I'm going to go up 1, 2 over 1. If you forgot how to do slope, add a little dash up here, then up 1, 2 over 1. And then I can do the mirror image on the other side. So I'm going to go up 2 over 1 this way, up 2 over 1 this way to make the V shape. And then my last step that I just did, step 4, was draw my line to make my graph. So that's pretty easy. We just determine our vertex, plot that, graph the slope, and then connect the dots. So I'm going to do one more example of that with you guys, or I'm going to try to do it as what's called a quick check. So if you want to try this on your own, I'm going to write the original problem, and then if you want to try it, pause it, give it a shot, and then I'll go over it. So I want us again to graph f of x equals -2 absolute value x plus 1 minus 3. So notice I changed a bunch of signs. So try that on your own if you can. Pause it if you need to. I'm going to go over it now. So step 1 is again determine A, H, and K. So I can see here A is equal to -2. H is equal to -1 because again it's the opposite sign of what's in there when I take it out. And then K is going to be 3, only -3. So that one keeps the sign, so K is -3. So then step 2 again is plot the vertex. So I'm going to plot my vertex here. So I have 1, 2, 3, 4, 5. So -1, -2, -3, -4, -5. 1, 2. Then 1, 2, 3, 4, 5, 6. That's -6 down there. So I'm going to plot my point -1, -3. So that's going to be down here this time. So -1, -3, plot that point. Now I'm going to plot points using my slope. So this time my slope is -2. So I'm going down 2 over 1 because my slope always tells me what's going on the right side. And I go down 2 over 1 again. And then I'll do my mirror image on the other side. So down 2 over 1 this way, down 2 over 1 this way to make the mirror image. Connect my dots, and I have my graph. So I've successfully graphed that absolute value function. So what I want to talk about now is some rules that we can sort of extrapolate from what we've been doing to make some larger generalizations about transformations. So transformations in math are the changes made to the parent function to make the other functions in the family. So I bring this up because what we're doing today with absolute value functions can actually be done to several different types of families of functions. So we'll learn about quadratic functions, exponential functions. Later down the line, you'll learn about trig functions and all those sorts of things. And they all have parent functions that undergo the same sorts of transformations that we were applying to absolute value functions. So I want to draw out what those changes are in a general context. Well, I've talked about them specifically for absolute value with a as the slope, h as the x-coordinate of the vertex, k as the y-coordinate of the vertex. I want to sort of generalize them in a way that can make them usable for all functions, even if they don't look like our absolute value function. So the first thing I want to talk about is a. So the sign on a determines if there is a vertical reflection. So you may remember some of these transformation terms from geometry, but a vertical reflection is when it flips up and down. So a vertical reflection flips up and down. So if the sign on A, if we have a negative A, that means it's flipped down. So for absolute value functions, that means it looks like this. That's why when we had a -2 here, it opened down instead of up. If we have a positive A, that means it's going to stay the same or be the typical look or open up or face upwards, so it's not flipped down. So it would be a normal V in the case of our absolute value function. But this is, again, the sign on A tells us that. Not A itself, but the sign on A tells us if it opens down or up, or if it's reflected down or up. A also tells us, so A itself determines the stretch or compression. So these are two different vocab words, stretch and compression. So we'll start with if the absolute value of A is greater than 1. So again, we're not worried about the sign here. That's why we're talking about the absolute value of A, because the sign is a different transformation. The absolute value of A is greater than 1. It gets steeper, which means there is a stretch. So if it gets steeper, if A is greater than 1, like it was with 2, it's getting thinner or steeper. It's a stretch, so it might look like a tighter shape than it would if the absolute value of A was less than 1. So if the absolute value of A is less than 1, it gets wider, which means it's a compression. So it sort of flattens out. If you think about the word compress, it flattens. So it might look more like that in terms of our absolute value function. But again, this works for all functions, not just for absolute value functions. The next one is, I'm going to skip over H for a second and talk about K. So K determines the vertical translation. So we'll start with positive K moves up, negative K moves down. So vertical again means up and down. So a vertical translation, that means we're sliding the whole graph up or down. So here, since it was -3, we slid it 3 units down. So normally our vertex is at 0, 0, but we slid it down 3 in this problem because of the K value. The last one is H. So H also determines a translation. Sorry, horizontal this time though. Sorry, I wrote that wrong for a second. Horizontal translation. So H determines the horizontal translation. So since our equation starts with a negative H, it's kind of backwards. So if our H is negative in the equation, so a negative H actually moves it right. So in the context of our problems, our negative H, if it's in the equation as a negative H, it moves it right. Whereas if it's a positive H, it'll move it left. So our H values are sort of opposites of what you would anticipate. So a negative h moves it. So if I slide this back up in the context of this problem, a negative, since this one's being added, I'd move it left. If it's subtracted, I move it right. So it's sort of counterintuitive. I move it in the negative direction if it's being added, in the positive direction if it's being subtracted. So the last thing I want to tie in here, I'm trying to wrap these up as quick as possible. These are all examples of vertical transformations. H is the only horizontal transformation that we're going to worry about this year. So vertical translation or transformations include all of those. Our only horizontal transformation is H this year. And the last thing I want to note is horizontal translation or transformations are written inside the rule or function rule with x. Vertical ones are written outside. And that's going to be important because when we see function equations written, it's going to be written inside with if it's horizontal, outside of it's vertical, so we'll be able to identify them in that way. All right, that's it for today. Make sure you write down questions, comments, and concerns so we can go over them together in class.